Hi everyone, I'm Kunal Deshmukh, third year PhD student at KU Leuven, and I'll be taking you a bit further than the galactic systems to 30 Doradus in the Large Magellanic Cloud, and I'll be talking about looking for O+ black hole binaries. So as the title suggests, that's kind of halfway to binary black holes, where one of the black holes is already formed. But just a quick recap of massive binary evolution, which we have seen, I think, a couple of times already, that if you start with two massive main sequence stars and you carry out the evolution, you see a lot of hoops the stars have to jump through. So marked in red are some of the very uncertain physics that all of us are trying to understand. And we also have some intermediate phases, for example, the strip stars that Ilva talked about, and we have some X-ray binaries and so on. So I'll focus mainly on the O+ black hole binaries. This is a phase that comes right after the primary is collapsed into a black hole, but before they start interacting again and show up as X-ray binaries. So observationally speaking, these binaries can show up as single line spectroscopic binaries, where if you take a spectrum of the binary, you see only one set of spectral lines moving back and forth, showing orbital motion. And usually when we see an SP1 system, that can mean one of two things, usually. One is that the second star is faint, so our data is not good enough to pick up signatures of the second star, and that is why it looks like a single line binary. But it could also mean that the second star just doesn't emit any light, and it's truly dark. In our case, we want to find black holes, so that's something we're looking for. And to do that exercise, we have to not just look at the spectrum by eye, we have to do some more magic using spectral disentangling, which I won't go into, but I'm happy to take questions about that. But what we do in this technique is we take the spectra of the binary, we take the known orbital solution, and what we try to do is separate out the two components present in the spectrum, assuming there are only two components. So this can either give you the second component, as in it can give you the signatures of the second component as spectral lines, or it can give you a nice flat spectrum, which means the second component is not contributing anything to the light as far as our noise is concerned. So this was done 3 years ago by Thomas Chenard and collaborators for 51 O-type SP1 systems in the 30 Doradus region. So for those of you who don't know, this is one of the most active starburst regions in the local group, has hundreds of massive stars, and is really the ideal place to look for such binaries where you have one massive O star and the other is a black hole. So they specifically looked at 51 SP1 systems because those are the prime candidates, and then they tackled it with spectral disentangling to see whether there are companions hiding in there. And what they found was a lot of these systems, actually, a lot of these SP1s were actually SP2s or double line spectroscopic binaries. So what we see here is in the blue we have the data at two radial velocity extremities of the binary, and if you look at just the blue line, it looks like a single line in both cases that is moving back and forth. But after performing this technique of spectral disentangling, what we can see is there are two components that are moving back and forth, and together they give us this blue spectrum, which means that a lot of these systems were actually SP2s masquerading as SP1s. So those we threw out, right? I mean, as far as black holes are concerned, these are not the ones we want. There were a few other systems that retained their SP1 status, but also there were quite a significant amount of binaries which were affected by nebular lines. So because we are looking in the Tarantula Nebula, the nebula also has something to say about what we are doing here. So usually, since nebula is made up of gas, and the spectral lines are also coming from certain elements like hydrogen and helium, these nebular lines can show up as emission lines and interfere with the spectra. They can be removed by subtracting the sky spectrum from the star spectrum, but that is not always possible if you look at the Tarantula region. What this leads to in terms of spectral disentangling is we can get artifacts which are not necessarily coming from a second star, but can look like a second star. So such binaries have been classified as uncertain SP2s, and we don't know for sure if they're SP2s or if they are SP1s that have been affected by this. So after getting rid of the SP2s, what we have now is a newly filtered sample. On the x-axis we see the period, on the y-axis we have the minimum secondary mass based on the binary mass function of each binary, and the shaded region shows the black hole domain. So if one of these binaries has a companion in this regime and doesn't give off any light, we can maybe start thinking it is a black hole. So we pick 15 candidates from this, and we go back to the Tarantula Nebula to see if we can get rid of this nebular contamination. So before I do that, there's only one confirmed system in this sample, VFTS243, also published by Thomas Shinar and collaborators, but a lot of these still remain uncertain. So we can't just throw away the sample, we have to go back. A quick recap of what was done in the previous study. Like I said, you need a spectrum of the star, you need a spectrum of the sky background, and you need to get rid of the nebular lines from the star using this sky background. But the issue is the intensity of the nebula varies drastically in this whole field. So if we have a star here, if we have our sky fiber here, what this means is that if the nebular intensity is different, we might get residuals when we subtract one from the other. Now, a solution to this is if we put a bunch of these fibers together and form what we call an integral field unit. This is not to scale, by the way. But what we do is we take a bunch of fibers, place it on the star. So the central fibers will catch the starlight. The surrounding fibers will catch the immediate surroundings of the star so that we can get as accurate nebular subtraction as possible. So the hope with this is to get rid of this residual feature and get really clean spectra where we don't have this uncertain sp2 problem anymore. So we did this with 28 new epochs spread over 2 years. The last epoch was actually taken a few weeks ago, and we focus on the S delta region in high spectral resolution. To show you an example of how these data look like, this is basically one IFU, and each of these is observations of these 15 stars. And each IFU consists of 20 fibers, so the 4 corners are empty. And these fibers, each of these pixels here, records a spectrum. So we are really getting a spectrum of the star that is located in the center and a spectrum of the sky that is located right next to the star. So it's not always centered, as you can see, but that is the idea that we are trying to do. So once we have our spectra, after subtracting the sky signal from the star, what we want to do is go through this decision tree of whether or not a companion is a black hole. So the first question we ask is, can the spectra be disentangled into 2 components? If the answer is yes, it is probably an sp2, we throw it out, or I mean we keep it aside. If the answer is no, then we have to ask the next question, can we hide a luminous star in the system? So we have an idea of the minimum mass of the secondary. So we can also have an estimate of how bright such a companion can be, depending on if it's a main sequence star, if it's a strip star, if it itself is a binary. And then we try to see if we can hide such a companion in the data we have. If the answer is yes, well, it's inconclusive now because there could be a companion like this in the system and we are not sensitive enough to see it. Could still be a black hole, but we can't say. If the answer is no, that is when we are a bit more confident that, okay, if nothing else can hide in this, it has to be a black hole, and that is the general philosophy behind VFTS243, which is the only confirmed one from the sample. Now, I'll quickly go over some preliminary findings because it's very fresh. The first thing I'll address is the nebular subtraction. Turns out the Tarantula Nebula is what's the word? It's complicated. And what we see here is, so I've marked in blue the star spectrum, which is what we have here. In red, so between the blue and red, we take the sky. And you can actually visibly see the nebular line is not the same in both. So the nebular line, even at such small scales, is changing, which means that if we subtract the sky from the star, we get this funny residual feature. So this was the problem we started with originally. And turns out, doesn't matter how close we go, this is going to be a problem. Now, fortunately, we have been working on modifying our spectral disentangling approach where we kind of exclude this region by deweighting it while disentangling the spectra, and then we can still get some meaningful idea about what these are doing. So, very tentatively, there are 3 new candidates out of our sample of 15. 4 others are likely sp2s, and some are still uncertain because the data quality is not good enough to say one or the other. So with this new approach that we are trying of disentangling by excluding this polluted region, we can actually go back to prioritizing high signal to noise instead of using these IFUs. And that will be key to confirm the unconstrained systems that we have now. So a little bit about how these fit into the modeling predictions will be covered a bit by Ug in today afternoon's talk, but I'll end it here and have any questions.
Thanks. Very nice talk. Because you already have the spectra, do you expect to see these O stars, if they are around black holes, like might actually look different than the field O stars, for example? For example, if they are strip stars.
You mean if the O stars are strip stars?
Yeah, let's say they have a black hole companion, right? And so it's probably already gone through some mass transfer. So then they're probably like more stripped than other O stars, right? Because you already have the spectra, can you actually see?
Yes, so for each of these stars, the idea is we are going to put together all the spectra we have to do a proper atmospheric analysis. I think for VFTS243, this was indeed seen that there was some enrichment of, I think, CNO elements that was a sign of earlier interaction. But that's something we have to do, but that will be done, yes. With this spectrum alone, it's a very small window, so we would ideally like as many lines as possible. But yes, that is a thing we will look into.
Thank you. Very interesting work. I'm kind of going to ask the same question that you just asked Joanna. All the SP2s that you kind of found or rejected, what are they? Are they interesting systems? And do you know what the, also with the disentangling here, can you say something about the companions that are not black holes?
I don't have an answer to that right away. Because we have not characterized the SP2s yet. When I say it's likely an SP2, what we get out of disentangling oftentimes, so if it's an SP2 where the secondary is contributing a lot, we can actually get an idea of what is the radial velocity of the other star as well. But as you go fainter and fainter, we stop getting a constraint on the radial velocity amplitude, and we can still get the presence of it, so we still get a signature of it, but we cannot constrain the velocity. So it's not easy to constrain the mass based on what we have. We can still constrain some things based on the flux ratio that we can recover. That is something we will do for the SP2s that we find. Yes, so I don't have an answer right away for now, but this is something that I think Tomer also did in his paper, characterizing the SP2, so we want to do something similar.
Johanna Müller-Horn. I was curious, I don't know if that's also part of Hugues' talk or yours, but could you say more about the candidates, O+ black hole systems, so their orbits and eccentricities? Do they look like the known O+ black hole systems, so circular and short period, or do you see?
All of them are eccentric. No, two of them are eccentric.
How eccentric?
Quite eccentric, 0.6. One of them is consistent with the circular, and the period range is quite scattered. I don't have them off the top of my head, but I think it's something that Ug will show plots of. Yes.
We have time for one more question. Well,
Norbert.
sorry.
Hey, Kunal, great talk. I was wondering, since these nebular lines are so pesky, are there any other spectral domains maybe we should consider where these nebular lines are not contaminating, but where the companions could contribute significantly?
That's a good point. So for what we observe for these nebular lines is as we go to the later lines, so alpha, beta, gamma, delta, I mean the higher order ones, we stop seeing them, but that also means we stop getting a good signal to noise because we are not as sensitive in that, at least with flames, for example. So I haven't thought about it as much. So there are places where the line will affect a lot less, but I'm not sure if there are places where the signal to noise will support finding such companions. Yes.
Okay, let's thank Kunal again.